All right, hell yeah. So we have material mechanics. This is James M. Gear, and we're going to continue our process of doing torsion. So hell yeah. So this is the chapter on torsion, and and I'm just going to kind of do a better job at reading the specifics and just reading the text. So where we're at in torsion is we're bringing in stress. And so let's just read through. And it says, and I think that's the hardest. And so what I'm going to try to do is work on, like, hey, if I want to say something, say it in about 3 sentences. So stress is the force divided by an area. So, and I relate this to moments. Moments in couples are maybe difficult to kind of mentally figure out what's going on, but still, moments are just a force, and two of them separated by a distance, or that's the definition of a couple. Two opposite forces separated by a distance. Just like if we see this term stress, I can still say it's a force acting on some area, and I think that is very helpful. I'm going to have to drink a lot of ice water tonight. All right, so that was too many sentences, so now we just got to continue. We got to start reading. Booyah. All right, hell yeah. So this says, now that we have investigated the shear strains, and that was when we torque on yeah, this is good, you know what I mean? If we have a cylinder and we torque on it, right-hand rule, thumb in that direction, fingers are going this way, the other one is going the other way. Hey, we're twisting this bar. Cool. Angles are going to form more on the surface, less in the middle. So that's kind of where we're at. Hell yeah. So now that we have investigated the shear strains, and even just that term right there, we have to stop and discuss terms, because shear strain, strain gets, its definition is like deformation or you could say that, but it's changes in length, and when we're talking shear, we're getting a change in angle. So hell yeah. So just like we have a steel bar, it changes in length. When we're talking shear, we have this little square. It's a horrible square, and then we have this square, and guess what? It turns into a diamond shape, and this is the angle that we get. And we've talked about how that angle is real small. And hell yeah. And then the small angle theorem says that, what does it say? This number, this angle in radians times this length is going to be the amount that it's going to be equal to that side. All right. Hell yeah. Let's, we really got to continue on. So, cool. So that we got to here. So that shear strains. The strain component is that angle, but this angle multiplied by that side can be easily seen as that portion that got raised up. Hell yeah. So, and that's going to happen in the circular bar and torsion. Not in the middle, all on the outside, and then linear, it's going to be a linear relationship. So anyway, we're going to see that. So this says go to figure 3.3 to 3.5. So we're going to do that. And so what do we got? So here is figure 3. Oh, yeah, they're just referring to those pictures that we probably just looked at. Hell yeah. So the directions of the stresses can be determined by inspection, as illustrated in figure 3.6a. So here's 3.6a. When we twist this thing this way, this side goes down. That's what we're looking at. When we twist this thing that way, this side goes up. Take a cylinder, like a foam. You could take a foam toy, you know what I mean, and then put a square piece, and then just draw a square, you know what I mean, on the foam, and then start twisting the foam, and hell yeah, you're going to get a diamond shape to form. This side's going to go down, that side's going to go up, this side's going to go over, and this side's going to go that way. But in general, what we're going to notice is that, that they're going to show it as like this shape. We're definitely, this side goes up, this side goes down. Yeah, I mean, you will get some twist this way too. But yeah, it's kind of interesting how they, you know, they kind of show these as parallel. But anyway, all right, hell yeah. Where are we at? So we observe that the torque T tends to rotate the right-hand end of the bar counterclockwise. We've talked about that. And then when viewed from the right. Therefore, the shear stress, that's going to be this tau term, tau, acting on the stress element, that square, we'll get back to that little square, located on the surface of the bar will have the directions shown in the figure. Okay, so sweet. Because this is twisting this little square that direction and that direction, you know what I mean? If I have material bending this direction and then distorting that direction, distorting or whatever you call it, it took a force to do that. So this little tau, that's what I say, you know, that's why I started with this. If you're just like, I hate this little letter, I do hate it. I hate the shear letters. You know what I mean? Tau, and then, what is that, a gamma? I still haven't looked up what the hell that is. It's probably not gamma. It might be gamma. Anyway, but yes, this is a force divided by an area. So, hey, just look at this little square and be like, hey, there's a force on it. And they're going to, in a moment, they're going to say, hey, like, this square has, it's a three-dimensional thing. It actually has some dimension into the cylinder, even if it's just one molecule deep. Like, keep that in mind. You know what I mean? Because the force that you would apply has to be on that surface, you know, that's cut in. We're just looking at the outer surface. This typically gets represented as a three-dimensional cube. I guess it doesn't have to be a cube. It could have, like I said, just like one molecule deep. But anyway, that force is going to be on that side, and that force would act on that area that you chose to make this little square, cube, or whatever. This tau is force divided by the area. So whatever area you chose to make that little square, we're going to take the force on that and divide it by the area. So hell yeah. Cool. And so that's what tau is. It's force divided by area. Cool. Therefore, the shear stresses, tau acting on the stress element located on the surface of the bar, will have the directions shown in the figure. Yes, so the stress, tau, is going to have the same direction that the force would be applied. You know what I mean? So that's always a good double check on reality. For clarity, the stress element shown in figure 3.6a, this little square, we're going to enlarge it to right here just so we can see what the hell's going on. Anyway, and that's going to be figure 3.6b, where both the shear strain and the shear stresses are shown. Cool. So we have this tau, we have this tau, this tau, this tau. Even just the fact that we have 4 arrows, you know, I graduated without really understanding why the hell you have 4 arrows. But I came up with a really cool, you know, I took a little balloon, and then I pinched here on this side of the balloon, just a tiny little inflated balloon, pinched there, and then I pulled down and pulled up. Well, you know what I mean? If I do that, I'm just going to rotate it. It's going to take no effort. You know what I mean? If I just do that in space, you could just imagine if this is a chunk of mass floating in the universe, and I put a little rocket engine there, that signifies this arrow, because the stress is signifying a force, but divided by the area, you know what I mean, whatever. So I can take this is a stress diagram. I can easily say this square is a cube and has a surface area, and if the shear stress is the force divided by that area, I can take this shear stress, which is force divided by the area, multiply it by that area, and get the force that we're talking about. And so cool. So I can draw a free body diagram where I'm putting a force down and a force up. Let's look at that. If I did that, put little rocket engines, one blowing this way, one blowing that way, you know what I mean? This thing's just going to spin and get faster and faster. Because this is a statics problem, I have to resist that spin. The only way to do that is put a force here and a force there. And because this thing is square, these are going to be, equal and opposite. This force and this force are this distance away, so that's going to generate a moment this way. It has to be balanced by a moment that way. Well, and the only place I can put forces on this top part of the square, and that's top part of the square, which is a cube. Never forget that. Anyway, and so I think that's very helpful to see a stress diagram and just to make your own force diagram. And I'm just always thinking about the forces. I have a hard time with this the stress aspect of things. Okay, so sweet. So did we learn anything from there? That this is the diagram. You're going to have 4 arrows on it, and they're going to be in that location. So if I do twist this, sure, this side goes down, this side goes up. Those are the 2 arrows that are obvious. These 2, the top ones, aren't as obvious, but I need those to, what I just said, counter that moment. And when this does deform in a diamond shape, we get an angle to form. Because this angle is so small, not that matters, but this is what we are going to measure. This is the measurable quantity when we shear something. We're just like, ooh, I see this. And there's one aspect of this that can be easily relatable, is that when we pull on something, like a bar, I can only pull it so far. I use the 1,000 millimeter bar, steel bar. I can lengthen it 2 millimeters, not very much. Okay, if I have this square, typically what you're going to be doing is like, hey, look at that. That's going to be the distance from that diagonal to that diagonal. And then guess what? So this, let's say this is 1,000. Cool. And then because I made it into a diamond shape, now it's here. And let's say this now is 2 millimeters. Well, that's as far as I can take it before this square's, this diagonal is going to get permanently stretched. So that's kind of in the nutshell how the derivation works. And you can do the calculations, and what you'll find is this is just 0.004, which means that if this is 1,000, then this height, I can see a 4 millimeter displacement in that height because it's small angle, 0.004 radians. Radians times the radius is the arc length, and that's going to be signified by that. Cool. So that's kind of in a nutshell. I don't even know what the hell we're talking about no more. But yes, this is the this diagram shows both the shear and the strain, and now we kind of have an idea of like how big the strain can be, and do we know how big the stress can be? That's the bummer. Like in with a steel bar, you can, if it's like a 1 square inch steel bar, you know what I mean, like that, then I can put 58,000 pounds. You know what I mean? That is the stress, and that stress, that's the symbol for the stress. Normal stress. This is the symbol for the shear stress. And the crazy bummer is they're just going to say, hey, maybe it's 50% of this. I think it could be as high as 80% or 79, or at least 78. If you run the calculations, 77.9, I think. But hell yeah. I mean, that's not for this video. Else we're just going to get into a rabbit hole of a fist fight. Because I swear, like the books just, that's where a lot of this is empirical. They'll say 56. They'll say 56% of this 58,000 is when you shear. So if I'm taking this block, and let's say this block is actually just a bolt, you know what I mean? And then I'm trying to shear it, put a force that way and a force that way, and trying to like rip it apart like that and shear. Well, I have an area of 1 square inch, let's say. Doesn't it take 58,000 pounds to do that? No, it's going to take a little bit less, and fractionally less. And one of the reasons, don't get too excited, but one of the reasons is if I did apply 58,000 pounds right here, the only way back to this little square, if I apply 58,000 pounds down and 58,000 pounds up, guess what? This thing's just going to rotate in space. The bolt that I'm trying to shear is just going to spin. You know what I mean? And so the only way to prevent it from spinning with a moment like that is to balance it by putting a force there. So that is the unlooked thing when we're trying to shear things apart. If I'm applying a 58,000 pound force downward and coupled with a 58,000 pound force up, you know what I mean? I think that was even a hard thing on a steel bar. If I pull 58,000 pounds this way, guess what over here's got to pull 58,000 pounds. And does that double it? No, everything just feels 58,000 pounds. But when we put this downward and upward, we have a distance here, and it creates this moment. We got to balance it. So look at this. We're applying 58,000 pounds. And that's where I just think this is just a really good thing to go over. You know, because the textbooks, they just go right to this picture with a tau, and no one likes tau, and it's all confusing as hell. And a tau is a stress, which is a force divided by an area, and the second you take a force divided by an area, I think you lose all, I don't know, it'd be like at the hardware store, you know, you buy a bolt, and someone's like, 1,000 pounds. You're like, sweet. I don't know what that even means, but I at least have a number that makes sense. Well, what if they said 36,000 psi? You're like, huh? Yeah, 36,000 psi. That's going to be the shear, because it's not going to be 58. It's going to be less, and that's going to be the pressure that that bolt can tolerate if you're trying to shear it. Well, no one knows what the hell 36,000 would even mean. 58,000, maybe. Like, hey, 58,000 psi, and I got an inch. Like, still, that's too far. You have to be you've had to graduate this course to even understand that concept. You know what I mean? You hand somebody a 1-inch steel bar and you say, hey, 58,000 pounds. They're like, okay, I can handle that. You could hand over any chunk of steel to someone and just say 58,000 psi and 36,000 psi, whether you're, tensioning it or shearing it. So that's the bummer about the shear stresses, and how everything is just in terms of stress. And yeah, I think that's why I failed the first go-around of this course. But yeah, that's why I like to think of things as force. So if I do have that bolt that's 1 inch thick, 58,000 pounds down, 58,000 pounds up, create that moment, I got to balance it. So look at this. I'm already applying another 58,000 and 58,000. Cool, look at that. So I'm just like, hey, didn't I just double the force with the same number? You know what I mean? It seems like I'm actually putting twice as much force on it. So sure, 50%. You might think that could be a good way to think of it. But these forces are getting applied at a 45-degree angle, so you only get a square root 2 of them. You only get like a 1.4, and then maybe inverse 1.4, and you get like a 0.7. 0.707, that might get you closer. But the actual Poisson's ratio, if you do the math from this textbook, you get 0.78, I think. I think it's like 0.79. If you actually do it. But then if you go to any Google search, if this is the normal stress and then this is the shear stress, you're going to get like a 56%. And that's a huge variation between 56 and 80 or 79 or even 76 or 77. So that's a 20% difference between maybe empiricism and geometry, because a lot of this book is just geometry. All right, so hell yeah. So now we really just have to move on. But booyah, we got like a paragraph. Hell yeah. So for clarity, I don't even know where we're at. So so this figure 3.6b. So both the shear strain and the shear stresses are shown. And so now we kind of have an idea of like, okay, the shear strain is that angle. See, I even hate that. Like shear means that we're dealing with like the little square that's getting, diamond shaped. The strain aspect is going to be measured in angle. The angle of that diamond compared to the normal strain, which was just that steel bar that got lengthened. And even normal strain isn't just the change in length, it's the change in length divided by length. You know what I mean? And so both stress and strain are properties that remain the same. So I can, yeah, this is good. It's just basic. I don't know. And it's just good for me to go over. So if this is a meter long steel bar, 2 millimeters, I can lengthen it. Okay. But let's say I have only a 500 millimeter, half a meter long bar. I can only lengthen it 1 millimeter. Okay, so if I have this square that's 1 meter or 1,000 millimeters, I can make it into a diamond shape where this is 4 millimeters. Cool. If I have something that's half the size, and this is only 500, I can make it into a diamond shape where this becomes 2. So then, what about this angle? You know what I mean? Well, this angle is going to be the same. We got to do small angles. You know what I mean? If you want to, it's always good to break out Pythagoreans. What we're saying is that this length with small angles, that length's the same as that. So if I just know this is 500, I'm going to say the hypotenuse is 500. And what are we trying to find? This angle. And what do I know about this? I know it's 1. And I'm sorry. Yeah, no, it's 2. It's 2 for this one. Because the angle should be 0.004. And let's see if we do get that. So how you would solve this is you would say, hey, the angle is going to be the inverse sine of 2 divided by 500. And what we would say is that... what we would say is just the sine of that angle. So get this to the other side. That's how you do that. Is just 2 divided by 500. And then, I always try to use as many skills as possible. But if I have 500 in my denominator, let's try to get it as a function, like a factor of 10, 100, 1,000. Multiply by 2, this becomes 1,000. But since I multiplied the denominator by 2, the numerator multiplies by 2, and then we get 4. 4 divided by 1,000 is 0.004, and we just showed kind of the small angle deal, because this is in radians, and we know that sine of an angle is, if the angle is small, is just the angle. You just get rid of the sine part. And then this one is 4 divided by 1,000. That's very easy to see, and we got that small angle. So same thing there. And then so when it comes to steel, hey, you get this angle to form 0.004. And when it comes to lengthening, well, what we want to do is, this is the normal strain, and that's going to be the change in length, 2, divided by the initial length, 1,000. Cool, and this one's going to be change in length of 1 divided by 500. Okay, let's get the denominator to be 1,000. This becomes 2, and we get 0.002. This, the length was 1,000. We can lengthen it by 2, and that's 0.002. So I can have any length, whether it's short or hella huge, and I just know that I can strain it in the axial direction by this 0.002. And if you hate proportions, move the decimal place 2, and you get 0.2%. And maybe you can remember that a little bit easier. Hey, if I have steel, 0.2%, that's how much I can lengthen it. It's also how much you can crunch it in the compression direction. Steel is just kind of cool like that. It's a good one to, yeah, that's why it's always good to use that as your basis. Hell yeah. All right, so we're not getting very far. This kind of, I don't know, I just always do introductory stuff, but that's fine. We're right here. And so we're talking about shear strain, the angle, and the shear stress. That's going to be the force divided by the area. And, and it's always good. Hey, this is our square, but guess what? It's a cube. And then the force would be here, and we're going to do shear force is V. And, shear force is V, but guess what? That has some area. And then so the actual, this is a free body diagram. If we actually did a shear diagram, we would say, hey, we have a tau here, which is the shear divided by the area. So that is kind of like, I have to do that every time, especially when reading textbooks, because I despise the word shear. I despise the word strain. Stress, strain, and then the fact that shear all have like these S-sounding, there's no, it's very difficult. Yeah, and I think most people, if you read this, shear, strain, I don't think angle just pops into your head. It has never popped into my head. Anytime I read this word shear strain, I'm just like, I give up. You know what I mean? I quit. And then but we're just getting slowly better. And maybe, and I don't think I'm alone on this, but I'm probably alone on this. I don't know if it's just the fact that I have PTSD, because I missed the first couple days, and that was dumb of me. I just missed the first day, but then I couldn't keep up, and I failed. And so that's why I love this course, because we took it again. Anyway, and then, so we have shear strain and then the shear stresses. Cool, and we know what those are now. Are shown on that blown up, enlarged square, which is a cube. As explained previously in section 2.6, we customarily draw these stress elements in 2 dimensions, that's square, as in that figure 3.6b that we've been talking about. But we must always remember that stress elements are actually 3-dimensional objects with a thickness perpendicular to the plane of the figure. So, I mean, I spaced out like halfway through reading that, you know what I mean? But that's what we've been talking about the entire time, is that this is a 3-dimension little cube. It's not the entire thing, so, I mean, you're just like, hey, there's a little cube. I don't know, but you got to make it big enough or small enough to make it make sense for what you're dealing with. But typically it's something that's small. It doesn't have to be like a calculus small, like a little differential. And that's the other thing, is like this book doesn't do it as well as Hibbler. Hibbler will say, hey, I'm going to take a little chunk, and guess what? That chunk is going to have dimension, and I'm just going to say it's going to have dimension change in x. You know what I mean? Hey, look at this. This is my x term, and then I'm going to come in here, and I'm just going to say this has change in x. And from the calculus perspective, that is way better than just automatically calling this a differential element. Because calling this a differential element, I don't know, like I'm a literalist. Like that literally makes my head spin, because it's not even a point. It's smaller than a point. And I just don't know if that's just the bipolar. A lot of people with schizophrenia also have words are so literal. So if you say there's an element that actually is so small that it approaches infinitesimal, like the infinitely small, then I will believe you, and it makes it no longer very tangible. Like if it's a magnitude of the universe smaller than what I just drew right there. So that's where it's just like, hey, that's at least, that's why the Hibbler book, they always start with, and most of the better teachers in calculus, they'll be like, hey, let's just call this some sort of element, because when you're doing the calculus, like you can make that element as big as you want. You know what I mean? You just get a crummy answer, but then you half the size of that element, and you're like, whoa, look at my answer. My answer got better. Let's keep halving that element, and look, it's still visible. It's not the tiniest bizarre speck of the universe, you know what I mean? It's not the tiniest, it's not infinitesimally small, and that's very useful. But as this approaches infinitesimally small, as this approaches 0, hey, then we can do the calculus. But yeah, it's just, I like the Hibbler book when they went over that. But I do like this book for its diagrams. I don't know, and this is the book that I started on, so I just get used to it. Hell yeah. All right, we are definitely not getting into this proof very fast. And we might not, now we're pretty much there. You know what I mean? I think we're at the point where we could read more sentences. Hell yeah. So that was, what are they saying? This is the sentence I spaced out on. It's a three-dimensional cube, whatever. So the magnitude of the shear stresses, okay, they're talking about those shear stresses, tau. Think force on the side of that area. Cool. And then the other thing about this is this is important. You know what I mean? Because if you have because this isn't a square, it is a cube, like friggin' A, draw the cube, you know what I mean? And then put a force on it. Or you can either put a shear force or you can put this letter tau, depending on whether you're doing a free body diagram or a shear diagram. Cool. And then if you do that, it has to have a complementary, moment balancing shear or tau. So there you go there. Okay, but a cube has 6 faces. So is anything going on this face or that back face over there? No. You know what I mean? What we know about shear stresses is that there can be no shear stress on a exposed exterior face. So if there is no stress over here, or let's just say there was, let's just say for whatever reason there is a force on this exterior face, well, there has to be a balancing force when we cube this three-dimensional object. Does that make sense? And I think that's useful when we look at, you know what I mean? When and I think it is useful to maybe even do hey, this is a square bolt, you know what I mean? Or just, you know what I mean? I don't know. I think a bolt is good because bolts get sheared, but we have a square bolt. And then we're going to try to shear it. So we're going to put it in some sort of vise, you know what I mean, where you have it's got nowhere to go. But still, if I'm putting an upward force on this line right there and a downward force on this line, well, it seems like these are just in line, but then we take our little square and then we realize, well, there's a distance between where I'm applying the force here and where I'm applying the force there. Because if these arrows are just right over the top, I'm just squeezing the thing. You know what I mean? So you can never shear something if you apply forces directly down and directly up. You know what I mean? If this was that same thing, it just won't split in two. You have to have some sort of difference in distance, even if it's not even tangible to see. But hell yeah. And so now what we're going to do is to take a look at not only a square right here, but a three-dimensional little cube. And so and then sometimes that's almost the differential part that gets you confused, because maybe the simplest thing is to actually just look at the whole cross-sectional face. So I'm going to say hey, this chunk right here has this face, and then let's give this face some thickness. So right there, I'm going to give that face some thickness, and that's going to be what we have. So I'm gonna, there you go. So here's our element, and then on this face is going to go up, and this face is good. And sometimes that's hard to even see. You know what I mean? If I have that face right there, guess what? That face is going to go down. And then if I have this face right here, you know what I mean? Separate, just think of them as little molecules, So you have a square patch of molecules there and a square patch of iron molecules there, and we got some metallic bonding. And then this one went up, and then the other face now went down. You know what I mean? So now that tripped me out with the not drawing this behind. Hell yeah. So there you go. So then you have the molecules in this phase. So that is what's happening. And then if we take a look, yeah, this is good, but I don't know. Maybe I'm just getting kind of confused too. Hell yeah. And then if I say this was the original face, you know, and I look at this little square, hey, now this square is now a diamond. So that is kind of useful. But just know that this little square right here could be the entire width of the bolt. That's what I was trying to get at. So even though we have a little square here, you could take the entire width of the bolt. You don't just have to, like, you know, pop in just a little bit, which kind of gets confusing. You can go in the entire way. And the same thing is going to happen is, so here's the diamond, and that's going to go all the way, and then on the other end. And then you have, so yeah, there you go. And you can make that, I mean, you can make this element as big as you want to get the job mentally done for you. All right, booyah. Okay, so, all right, so the magnitude of those stresses can be determined from the strains. Okay, so we have this idea of Hooke's law. You know what I mean? We just said if we have a square, I can go 4 millimeters right there if this was a distance of 1,000. Hell yeah. And then so what we have is, what were we saying? Let's say this chunk is has a surface area of 1 inch. It's a 1 inch bolt and we're trying to shear it. And then so what I'm going to do is I'm going to apply a force on it, V. And then so because I'm dealing with a 1 inch, the shear is also going to be this force divided by 1. You know what I mean? So that makes it easy. And I don't think I'm going to get there. Oh, yeah. And then we actually just do this in the lab. That's the other part about it. It's the it doesn't really matter what the hell the percentage is anyway. It doesn't matter what we even think is going on at the molecular level. Because the cool thing about materials is for actually just using them for their strength, when I do apply a force, let's say I apply 0 force. 0 force there, 0 force there. It's a cube. Let's say I apply 1 pound of force. Cool. Guess what? It now turned into a diamond shape. Even with the smallest quantity of force, it's still making a diamond shape. That is a cool principle of materials, is that there's, for all intensive purposes, from a classical Newtonian perspective, is it's not quantized, you know what I mean, or it doesn't take like if you put any sort of force. That's why I mentioned just like, hey, if you got a tank, you know what I mean, and 2 people push on a tank, you know what I mean, one side and the other, that tank now like crunched in. It's no longer this initial length that it was before 2 people push on both sides of a tank. So there is that property, and then the one property that they're talking about is this linear, and I think that's very fascinating. And I think I can explain it from rubber band. Like rubber bands is like, hey, if I have this rubber band, it can lengthen about 8 times before it might break. You know what I mean? So it has this property where it can get 8 times its original length before it maybe breaks. So that's pretty cool. And what's going on? And it's linear. If it takes 20 pounds to break a rubber band, and I lengthened it that distance. If I lengthen it half the distance, that's 10 pounds. If I lengthen it a quarter of the distance, that's 5 pounds. So that's happening with materials. So if I do have a tank that's 10 meters long, I can shorten it or lengthen it by 20 millimeters, about an inch, you know what I mean? And so if I just put a little bit of force on both sides, it's going to shorten by a certain amount. I get 2 more people, pushing on both sides. It's actually going to shorten by now double. So if 2 people push on a tank, at this molecular level, it shortened that much. If 4 people push on a tank, it shortened that much. So we get this linear relationship, and this linear relationship stays linear up until pretty much like you pretty much for the numbers you would design for building stuff. Like you get all your strength in this linear range and plenty of it to design stuff in that linear range without so that kind of, even though things can get into the plastic range, and by design they do sometimes, but I think for the most part you don't have to stress out about that a whole lot. Anyway, but hell yeah, so you have this idea that you put a little force on something, you do get a little bit of movement. You put the max force, the force that's either going to pull on a bar and break it, and a bar just goes plastic. That's why I hate like engineering and physics. Is just like, it's just kind of like what I do in my head is just like, hey, if I stretch a steel bar by that a meter long steel bar 2 millimeters, in my mind it's broken. Even though I just know it's going to bend permanently, and I can almost stretch it 5% of its length, which is 2 inches. That's crazy. It's going to be totally worthless after that. It's going to be neck down, but it does pick up some extra strength. You're kind of cold forging it. But anyway, what I like to think of at the top of the linear range is just like, hey, either things break or you lose your job or someone lost their life. That is very useful because then it keeps this ceiling on things. And then so when you see like shear max, you know what I mean? Now I can think of like, hey, that's the max number where if things go above that, hey, people died. You know what I mean? And then the shear stress, that's force per area. Shear max, hey, that's the max. And they just use it in the engineering senses. That's the max. That's the highest end of the linear range. After the linear range, you are going to get permanent bending. Like your tool is going to be bent. Your bridge is going to be bent permanently. You know what I mean? It could be a ways to go before things actually fail, break, and kill people. But I think at the top of that linear range, it's good to have that in mind. Else these terms of just like, hey, shear max, I don't know, unless you like, put some sort of emphasis in your own brain of like what that means to you. You know what I mean? Are you a scientist and you just know that's actually just sheer what do they call it? Proportional limit, PL, you know what I mean? Because there's some things are linear up to a point where it's just like then you actually it'll stretch out just a little bit, you know what I mean? And so without any more load, so that you get to the point where you're like, woof, you know what I mean? It kind of turns microly plastic. And I guess that is the plastic range, where after that, some materials have a larger proportional limit, if I'm getting that right. And then you'll start, the molecules will actually fill in voids and realign and become stronger, and then so you get this extra bump of strength. Things get thinner, you know what I mean? And therefore thinner means more pressure, I don't know. It's like the fact that you are actually getting a thinner tool or thinner bar that can hold more strength, well, it's just like, why didn't we start with that bar to begin with? You know what I mean? So that there's forging processes that could, fill in those voids and make sure everything's structured and aligned. But you do get that extra strength, so it's always good to look at. All right, hell yeah. So anyway, so that's the linear part of this. So now we're going to talk about, so it says the magnitudes of the shear stresses can be determined from the shear strains. Oh yeah. So that's the fundamental of material mechanics. If I have this 1 meter bar, and it's 1 inch thick, I can hand it to you and say 58,000 pounds. And I think that is what most people can handle. I could say 58,000 psi because the area is 1 square inch. And then that number can be synonymous with any steel bar of any size. Cool, we talked about that. But if I just say 58,000 pounds, like hell yeah, you kind of know what you're dealing with. If I say this bar, if I hand you a bar and I say 2 millimeters, then you're like, what the hell are you talking about? Well, I say, 2 millimeters is what this bar can lengthen. After it lengthens, you probably killed people. And you're like, well, I can't measure 2 millimeters. How the hell am I going to actually put this into production and hang something with it or do whatever I want to do with it and keep track of that change in length? It's not happening. But that if we were just like robots, where you're just like, oh, I can see everything, and then if I actually do put it into practice and load it up and stuff, and then input in my brain gives me a number, and I'm like 1.7. Okay, well, we're about at the limit, you know what I mean? So let's stop there. Or, would it make more sense if I actually put it into production and then actually had those scale devices that make all YouTubers rich, and then it said 40, and it said 48,000 pounds. I'd be like, ooh, we're getting close. You know what I mean? So that has more bearing in our brains than this idea of changes in length. But this is the fundamental property of material mechanics. If I hand you a 1,000 millimeter or a 1 meter steel bar, and I say 2 millimeters, I can say 2 millimeters or 58,000 pounds. Those are the two properties I can give you. One measures, and they're the same. So if I say, hey, only go up to 1 millimeter on this steel bar, that's the same thing as only go up to 29,000 pounds, just half of 58,000. Those two are synonymous. If I say, hey, we need a factor, and this would be like the limit. This would be a factor of safety of 2, because I could go twice as much. Hey, I want a factor of safety of 4. I'm handing you this 1,000 millimeter by 1 inch steel bar, and I say, what the hell is half of 29? 15? 14.5? So if I'm going to say 14,500 pounds, that's your limit, and I'm going to say 0.5 millimeters. That is your limit. And you see that we get we already talked about this linear relationship, and I did want to talk about rubber, because rubber bands, once it stretches out 8 inches, then your bonds become covalent. I think rubber is covalent. Anytime I say just anything about chemistry, do not take it for granted. But what's happening before this thing gets fully stretched and your bonds become covalent and can't stretch hardly a darn after that and then snap and break, what's happening is all the rubber molecules, this is a rubber molecule. Cool. And then here's a rubber molecule. You know what I mean? Every rubber molecule is kind of folded over 3 times, maybe 8 times, you know what I mean? So just think of a rubber molecule being like that, and then here's another rubber molecule, and, it's just folded over 8 times. And then so when we stretch a piece of rubber, all of these, here's the bond. There is the actual bond between those. This is just kind of the structure of the molecule folding around itself. So as when we pull on the rubber, that structure unwinds, more and more, and then has its full length. You know what I mean? So it looked like this, and now we're taking it and making it like that, and we get 8 times the distance out of it. And I think, because I'm always trying to, like, now from this point I'm just making up stuff, but I'm not on this rubber, but what I'm going to talk about for steel, because I had to look this up, because 2 charges, if you have a positive and a negative, and this is how the universe is, like, structured, and there's a force between those, an attractive force. If I move this one just a little bit, and then that attractive force goes down by 10 whatevers. Cool. And then I'm going to move the same distance. Does it go down by 20? Now is it negative 20? Or does it go down another negative 10 if I move the same distance? No. It's not linear. It's inverse square. And you have, so that is not a linear, but what we find, can I undo that? Nope. Oh, hell yeah, I can undo that. Yeah, so what we find with materials, because iron atoms and steel is just molecules in a sea of electrons, you know what I mean? And then so you have the positive charges of the actual mass part of an iron atom, and you have these sea of electrons. Don't quote me on this, but anyway, so you like metallic bonds are charge related, but what we find is that through the strength of a material, from having it and then doing what we want with it, it's a linear process. So I would just suspect, and the literature says, like the very basic Google AI says, like the linear process is just a slight restructuring of, not restructuring, because after you get past that linear range, you get into plastic range, and that's permanent deformation. That's like if you have, like, hey, we have a void here, like this was the actual diameter of our specimen, and after we pull it, hey, this molecule jumps in there, and now we get something thinner. But we get something stronger because we're filling in voids and kind of cold forging having a stronger material. So that I would call, I don't know what terms they use, but I would say that is dislocating. I think actually whatever that called, that's filling in voids. I think they do use just, if I got some steel and you got this going on and I'm starting to pull on it from the linear range, and I can take it from this length to just, 0.2%, not very much. But what happens is that these are getting, do they say dislocations? I forget what term they use. But it could be very similar to what's happening to the rubber band, is that you're getting movement of those molecules right at the point of, like, you know what I mean? They're kind of at their limit. After that, they're either going to break, which covalent bonds do. They just break. That's where steel is just fascinating. You get up to that linear range and you get to the proportional limit, and then you get extra strength. Well, that's just because those bonds can fill in voids, and you are forging. You're getting but if you just have glass is going to go up to there and break. And now is glass covalent? I don't know. But like salt is I don't even know what the hell covalent means. But anyway, but you can just imagine that some bonds have a linear range and then just instantly fail. But still, I think, and this is where I would love to take like a PhD course on the actual nitty gritty of what's going on at the chemistry and molecular level, and then continue that science, because I think you need it. I think someone needs to give you a crash course into the latest and greatest of what's actually happening at these molecules. And because I swear, like, there's not even the basics. Even what I'm telling you is just made up. You know what I mean? It's just like my best explanation of like what I think would be a good explanation. And it's just the best explanation I have in my mind, because I think you do need at least some explanation, especially when we have a linear relationship for something that should be inverse square. Yeah, that is fascinating. And for something that can actually gain more strength after, relocating. And so you have a lot of dynamics going on. You're still dealing with things that are inverse square. There's still electromagnetic, metallic bonds are still like electromagnetic in nature, I think. Again, I could say I think after every sentence I talk about when I'm talking about this stuff. So anyway, but hell yeah, it's linear. So that, so that's what, the take-home point on this is like, yeah, I hand you a piece of steel, I can give you a poundage, or I can give you a length. And since we're talking shear, I can hand you a bolt, a square bolt that looks like this, you know what I mean? And if your objective is to try to shear it because you're going to insert it into, something that is actually applicable for that, that might get sheared, you know what I mean? You need this to have strength, and that's the surface that's actually going to get sheared. And so if I hand you this bolt that's a 1 inch, like this is going to be your 1 inch area, and I say 36,000, and I'm just making that number up. I mean, I'm sure it could be from the 0.7, I think it's like 48,000 or, closer to that. But let's just stick with 36, because it could be as low as half of 58,000, which is 29. So there you go. So 36. If I say 36,000 pounds, cool. So not only, are you going to have to put 36,000 pounds this way, but you have to balance that with an opposite force, and then you have to actually, and that would just spin it, then you actually have to, and that's going to generate a moment this way. You actually have to put a force this way and this way just to make sure it doesn't rotate. You know what I mean? Isn't that wild that that's happening? Like when we shear something, do this with like a piece of crayon or a piece of chalk in your hands. If like one palm goes that way and the other palm goes that way, or fingers, just note it, especially using, like I was doing like big old sidewalk chalk. What I noticed, palming it in one hand and palming it the other half in the other hand and shearing it, is like you're literally pulling it up at a 45. It's almost impossible to purely move up and down on a vertical line, because it requires whatever force you're putting down and up, it requires this left and right force. And because these forces are just vector arrows and obey vector addition, look at this. I'm going up and then this way. So this force goes up and then this way. The resultant is at a 45 that way. This force is going to be shearing down and that way. So guess what? Down and that way. And then my resulting force is at a 45. So that happens without you even really realizing it. And we got to get that picture back. I was just trying to... Whoop. So why did I bring this up? Yeah, so I could say 36,000 pounds. But the other thing I can tell you is I can give you this number, 0.004. And now this is going to be, this is good to go over, because it almost is nonsensical, or it's very difficult to visualize. But to visualize this, and this number, and the other aspect that I didn't talk about, is that if we are in the linear range, I can take this 1,000 millimeter, 1 meter steel bar, lengthen it by 2 millimeters, and guess what? So that's going to require force. But when I do apply that force to 2 millimeters and then stop the force and just let go, this thing goes right back to the original shape. So keep that in your mind. If you are in that linear range and you let go of the force, every molecule goes back to its original location. It's very fascinating. And then that's just cool too. So that's also what this 0.004 angle means. And what we do is we draw a little square on this, and I say, hey, if this angle if you can register that angle of 0.004, which is very, very small, it'd be hard to calculate, then this thing, you better stop and then let go, and then you'll just have the original bolt. But if you go farther, then what this bolt is going to do is going to start permanently, start permanently bending and becoming a sheared bolt. So yes, but if you take this angle and you can measure it to 0.004, if this is steel, you will get this shape to form while you're bending it. But then if you let go, guess what? It just goes right back to every molecule being in its identical location. So that is fascinating. And you don't even have to go to the max to notice a little change. I can put any sort of shear force. I can put the tiniest amount of shear force, and that little square is going to turn into a diamond, because on these surfaces, down arrow, up arrow, and shearing, you know what I mean, and left arrow, right arrow, that little square is going to get sheared. It's going to turn into a diamond shape. But it's just kind of interesting that if I set this into a vise and tried to shear this bolt, this would be totally flat. I would have a flat surface up here pushing down, flat surface here pushing up. And so and like I said before, you can't have forces, you can't shear something if the forces are dead vertical. So you still have to make them slightly difference, so they can slide past each other, at least one molecule of difference. And so when we do that, I at least have a few molecules that are square and then can bend at that angle, even if every other molecule's right and left are bound by the vise or the device that's holding them square. You know what I mean? That's fair enough. But along that shear, you are going to get elements that are going to turn into a diamond shape. A square turns into a diamond, but if you're not at that 0.004 limit or past, you can let go of the force and every molecule goes back totally straight. So that, I don't know how you or why you would want to teach a textbook if you just didn't, say, hey, we're now talking about Hooke's law, and that whole process is just called Hooke's law. And I also hate that. It's like one of my biggest pet peeves of physics is that, two pet peeves. Well, I don't know. Maybe Hooke's law is better. Like, I hate the fundamental theorem of calculus. That's worse than calling something's Hooke's law. And I'll explain both. One, the fundamental theorem of calculus tells you zero. It tells you absolutely nothing. And I think it's just the fact that, I even have to guess what the hell it is. What if things are continuous, then you can integrate? I think that's the fundamental theorem. If you have a function that is continuous, it's integratable. I think, why don't they just say the continuous integratable theorem of calculus? You know what I mean? That would make more sense. Same thing with naming things by the person. It's not very helpful. You know what I mean? You could call it the linear law. anything better than Hooke's law. But anyway, I don't even know who Hooks is. I should look him up. I bet you he's a pretty cool person. So, I mean, if I got named something, hell yeah, what would we do? Stage name, Dex, the Dex law. That's the comedian name I go by. Anyway, yeah, just naming things by people's names, it's not very useful. Anyway, but that whole process of Hooke's law is the fact that I can give you a material, I can give you the poundage or the change in length. Cool. I can give you the shear poundage and the angle change, which we're calling gamma. And see, I'm just used to an angle being theta. Gamma is very difficult for me to see that that's an angle. Anyway, but that's Hooke's law. And again, it's a lot easier if someone just says, hey, and I didn't even say it right. Hooke's law at its fundamental is handing you a piece of material and saying, hey, here's a chunk of steel. I'm going to give you a PSI and a length per length, a meter per meter. So this is going to be your change in length per length, and this is going to be your force per area. That's for normal stress. And then for shear stress, same thing, force per area. And we're going to get a radians, which, if your angle is small, look at this. So if here is your small little angle, well, this angle, I mean, how would you find this angle? You would take the inverse sine of, I'm going to go A, B, C for the hypotenuse. You would take the inverse sine of AC. Cool. And that is going to be this angle. But then I can take the sine of both sides. Cool. And if I do take the sine of both sides, sine of inverse sine, that just goes away. And then I have sine of the angle is A divided by C. If this angle is small, C is just B. So then I have A divided by B. And cool. And then if this angle is small, the sine is, that's the accurate way to do it, sine of the angle always. But you don't have to, because you can just say, hey, this in radians is just A over B. So literally, that's the other thing is that, hey, if I have shear strain, this is shear strain. See, I can't say that without even understanding what we're talking about. So it's shear, so it's the square. It's the strain, so we're getting that little angle to form. And this is an angle. And I can say the units on it, look at this, are meter per meter, even though it's units of radians. But because of small angle, it's meter per meter. So there you go. So if I hand you a piece of material, I'm going to say PSI and then meter per meter. I'm going to give you a value in PSI, and I'm going to give you a value in meter per meter. Or I'm going to give you a value in PSI, and I'm going to give you a radian, a number for radians. So this is shear stress, and this is the angle in radians shear strain. This is normal stress, and then this is the change in length per length normal strain. But man, I just think material mechanics, it's a mouthful to say those. Normal stress, normal strain, shear stress, shear strain. And even just to say them and then mentally say, if I say shear strain, that's going to be an angle. It's like thinking about that in my head. Shear strain is an angle. Nothing gets there for me. I'm literally, the only time I'm saying shear strain and then thinking about it, I'm just trying to say the word shear strain without calling it shear stress or normal strain. You know what I mean? I'm just trying to actually say the words correctly. And that's a bummer, because if the words are so hard to say, then the interpretation or the actual definition defining those words get lost. And so I don't know how you would, that's where I just kind of stay away from these terms if I can, as much as possible, or just mentally, if I see this, I'm thinking, hey, a shear force caused this angle to change. But I even know that I have to get better and always, like, even when I see this little term, like, I don't even see this Greek letter as an angle. Like, that's a bummer on me. I see this as an angle, theta and phi, you know what I mean? I definitely see those two in phi or phi, you know what I mean? And then saying the word shear strain, I just, it's like a puzzle in my head. Every time saying the word shear strain, that is as a puzzle. I'm talking about shear, and then I guess I'm talking about that angle. So I definitely need to get better and faster at saying shear strain and envisioning this gamma, visioning this angle, visioning this small angle. It could be a meter per meter, but yes, shear strain. Just kind of like I'm doing it right now. I see the diamond, I see the square becoming a diamond. Shear strain is the angle. It's a small angle, so it is still related to that change in height divided by the radius, you know, the length. Hell yeah. Another way to look at this is like, hey, this is in radians, so radians times radius is arc length. So I could say radians times b is equal to arc length a. So then rearrange, and we have gamma is equal to a divided by b. So a lot of different ways to get there. I think the slowest approach is doing a right triangle, setting up some hypotenuses, doing it textbook where you have a sine of an angle. You could also, you could have just done the tangent, because like I'm just given this, I'm given b anyway. But it seems like that's not technically correct, because even if we come down here, you know what I mean, this square, this length AB now becomes AB prime, which is a hypotenuse. So this angle is related to the sine, like this new length, and this arc length. But even a right triangle doesn't have an arc length. The arc length is for a circle, so it's just approximation. But with a small angle, the arc length, if I, and it's always good to even do that instead of just say the words. Like if I take this as my radius, or even if I take this diagonal as my radius, and then draw a circle. There you go. So this hypotenuse, this straight section is a little bit shorter. This is the radius of the circle. This gets dropped down straight. The arc length is a little bit longer than that little thing. But if this angle is small, those two are identical. All right, hell yeah. Okay, so Hooke's law is that whole idea of handing you a number for stress and a number for the angle change. We're only talking shear in this proof. So it's the PSI that you would put, if this was our square bolt, it's the PSI that you would put on this area, and it's the shear force. So I'm going to apply a force onto that area. That is the shear stress. When I do that, sure, I need to apply the same force over here, and guess what? The area is the same. Cool, so then that's going to be the same tau. If I do that, and this is a good one to go over, so if I do that, I get this moment, or I get a torque or a moment, and I need to balance that by going this way. And so the only place to do that is on this face. And then we're going to do a shear force there, and those shear forces are the same value, and they're associated with a shear stress because they operate on those faces which have areas, and those areas are the same. So therefore we get all four of those shear stresses, which is the PSI buildup on those faces. And then I am going to go over this because if I'm at the bottom of the ocean, these are water molecules, and then you just have, you know, a column of water all the way to the surface. And if I'm right here, you know what I mean, I'm getting pushed in at all, well, I guess, I'm I'm just relating normal stress. So like, well, this is actually what do they call this? Hydrostatic, where actually the pressure is all over. It's actually 360. When I have a steel bar and push in on the ends, like in compression, you know what I mean? Like on this face, I'm just pushing in on like let's say two square discs of molecules. Those molecules are just getting pushed in. Each of the molecules between those discs are just getting pushed in this way and this way. When I shear something, you know what I mean? So this is let's say the square bolt again, but it's just 4 molecules. These molecules go up and these molecules go down. I'm not necessarily, these molecules aren't getting farther apart or closer together. They're just moving laterally compared to those molecules. So I guess I am getting better at being okay with the idea. I don't know, you know what I mean? But sideways pressure is that I'm putting a force right here, and that force is on that cross-sectional area. I still think it's kind of a made-up term for shear stress, which just makes it even worse. But what we're saying is if I'm applying a shear force, I'm relating it to the area that I'm applying that force. Because if I double the area, then the pressure reduces by half. You know what I mean? So there is that relationship that if I have more material, twice as much material, same force, the PSI is half. And if it takes a max, if it takes this big number to actually get that square bolt to shear, and then I just doubled the size of the bolt, well, I need to get and that PSI with my normal force is just this number. I need to get it to that number, twice as big, so I need to put 2 times the force into it. Hell yeah. I really do think this is good for me, though, to just go over these, kind of basic concepts. I don't think they're basic at all. I think all this is heady as hell, and I think the basics just get, just word sauced in, just textbook style, where everything is just too, just kind of too professional, and you're just like, I don't know. It's just like, yeah, I just throw things on repeat until they sound like they don't make no sense. I don't know how to say that. Anyway. Okay, so hell yeah. So that is Hooke's Law and shear. And we're applying the shear stresses. So the magnitude of the shear stresses can be determined from the strains. So if I have this cylinder and I can register the angles on some portion of the outside portion of the cylinder, let's say, or the shaft or whatever, and I can see an angle form. Cool. I can use that angle. I can measure that angle. I mean, but that's the bummer. It's like we just talked about how those angles are difficult to measure. But let's say I measure an angle of 0.001. Hell yeah. It sounds like I'm a quarter of the way from wrecking this thing. I can go 4 times as much force. So whatever I'm doing, I'm cool. I got a factor of safety of 4. And if I can register that angle, it's related to a shear stress of, let's say, I don't know, 10,000 pounds. You know what I mean? So hell yeah, we can go 4 times as much on that. And so that is the whole idea of relating Hooke's Law in shear, is that if I see an angle form and I can measure it, and I know it's a quarter of the way to that angle can be anywhere from 0 to 0.004 for steel, let's say. And so if I measure the angle somewhere there, that number is proportional to what the stress is happening in that thing. Cool. And again, the stress is like, hey, if I see this angle to form and it's 0.001, what I know about this cube is that the stress, I know the stress, so 0.001, if it was 0.004, I know the stress is like, let's say it's just 40,000, and it's 0.001, so I know the stress is 10,000. 10,000 psi, which is pounds per square inch of shear stress. Shear stress is a force on a sideways area. It's bizarre as hell. But still, I know that this is 10,000 pounds. I know my square bolt is 1 inch. So guess what? I know there's an upward force of 10,000 pounds on that thing. That's significant. Hell yeah. And that's for a square bar. So yeah, but that is the fundamental that I think gets lost unless you talk your way through it constantly. Yes, because this says, you know what I mean, from determination of the strains, which for shear strains, that's measuring an angle. I can take that angle of 0.001 and say that the stress is 10,000 pounds. If I know the stress, then I know the shear forces. You know what I mean? We did that. But here's that relationship. Oh, and the other thing is if I have this number 0.001 and then I get a number of 10,000 pounds, and those are synonymous, or if I have this number 0.004 and then that's equivalent, that's the angle form, but that's going to be associated with a pressure of 40,000 psi. Well, these two numbers are synonymous. You know what I mean? 0.001 is basically, you know, kind of quote unquote equal to 10,000 psi. 0.004 radians is equal to 40,000 psi. So that's where you need a conversion factor. If I say 0.004, what number do I have to multiply by 0.004 to get 40,000 pounds? And this is where scientific notation works very good, because I got 1, 2, 3. This is 4 times 10 to the negative 3. And I could just move decimals, like 1, 2, 3, 4, 5, 6, 7. So let's see if I can double check my answer. This is 4 times 10 to the negative 3. This is 1, 2, 3, 4. This is 4 times 10 to the 4. And so what do I need to multiply this to get to that? I need to have 7 zeros. So I need to multiply by 10 to the 7. And that's what we just said, 10 to the 7. So 10 to the 7 is the number that I need to multiply. So again, this is an equation. It says, hey, if I have shear stress, and this is just for the max, you know what I mean? If I have it's for anything, because if I have 10,000 pounds, I know that's going to be 0.001. So I need an equation where if I can throw in this number, I pop out that number. Or if I, for the way they are saying it, if I measure this angle of 0.001, I'm going to input that, multiply it by a constant, and then pop out this number. And that's what this does right here. Here's my angle of 0.001. My G is 10 to the 7, and then this becomes 10,000. If this is 0.004 times 10,000, this becomes 40. If this is 0.004 times 10 to the 7, 10 to the 7 would be our G that we calculated. This becomes 40,000. So, hell yeah. But that doesn't get explained as much as it needs to be. Even just this Hooke's law of like, what you got going on? Because you have this is psi. This is an angle in radians, which is basically dimensionless. And then you have this, which must be in psi. I mean, but cool, that just makes the units come out. But then what the hell is this equation? Well, it's trying to relate That's the whole idea. I graduated without really understanding this Hooke's law, and that's the whole fundamental. I hand you a chunk of steel. I can say 58,000 pounds. I can say 2 millimeters. I can say 58,000 psi, and I can say 0.002. You know what I mean? And that's what we're getting at. In shear, if I hand you that 1-inch square bolt, I can say 0.004, and then I can say 40,000 psi, let's say. That's what we've been trying to do with this. And then so at least know, and I've never memorized G. I've memorized E for steel is 29 million. But G, well, hell yeah, I know it's 10,000. Close enough. You know what I mean? No, I know it's 10 million. Sorry about that. Yeah, that's 10 to the 7. Is 10 million. Cool, good to know. And I think it's 11 million. You know what I mean? Just to dial it in. Okay, hell yeah. So, again, we're just reading textbooks, and we're just covering kind of the fundamentals, but it's very important. And that's it. Look at that. We haven't even got... We just got to explaining what the hell Hooke's law is. And I am definitely running out of gas, and no one's going to watch 3-hour videos. So, we are going to leave. But that was totally necessary. Because I swear, this tau term can end you. You know what I mean? Because it's just like, one, it's a shear stress. 2, it's a force divided by that area, and that area is a sideways area, which is a pressure that's sideways, which is bizarre, and sounds made up as hell. But, like we said, we double that area because we doubled the square bolt. Well, then it requires, we need twice as much force to get this to max out. The other thing that we have said so far is that, you know what I mean? Hey, we know that this has a max, and we know that at the max, this is still linear. Things are going to bend, and then when we let go, they're going to go back to their normal shape. And because we're talking about shear, we kind of have a square that's getting diamond-shaped, because we're taking a square bolt, and it's three-dimensional, you know, so we're taking our three-dimensional square bolt, trying to push up and down on it to shear it across this face. We're going to get some sort of angle to form, which is that diamond shape. And so again, if we let go, it goes back to the square. And if we apply any force at all, we for sure get a slight angle. We get a diamond shape no matter how much, you know, shear force we apply. The other thing is if I'm applying an upward and downward, that creates a moment this way. So I need my 2 other arrows that way and that way. And just the fact that I'm shearing something, if I'm pushing up and down with what I would register as known forces that are like, yeah, those sound like they're the forces that are shearing. It's bizarre that there's an equal force sideways to keep that thing from rotating. And because we're doubling up on the force, that is one aspect where shear, like this quantity, this number in shear is less, can be less to 56% to 79%, you know, 20% different. I mean, but yeah, that's the range that shear is going to happen easier than being pulled apart in tension. Cool. But if I apply any of those numbers at all, I am going to get a little angle to form. If I apply 0 force, 0 angle. If I apply the max force, I get the max angle. That's a linear relationship, and this is the linear equation. If I apply 0 and 0, that graph goes through the origin. Like 0 force, I'm getting 0 angle. So therefore, this is like a y is equal to mx plus b, because my y-intercept b is 0, so this is a y is equal to mx graph. And then so if this is the tau, that's the y part, g is the slope, and then this is your angle. So if my angle is my independent variable, which they've been talking about, and it sucks because no one's going to measure the angle, the only way to actually measure anything in material mechanic world is to put little strain gauges on, which are tiny little wires, manufactured wires so small you can probably hardly see them. But then when you tape them or glue them onto the surface of the metal, and things happen, and they're going to be crisscrossed, applesauced, and then or just have 45-degree angles, like this and stuff. You get a little rosetta. Hey, if I'm pulling this way and this way, these are going to lengthen. Poisson's ratio says that the area is going to neck down, and it's going to get smaller. Electrical resistance goes up, and we can measure that to a high degree. But literally, if I just hand you a chunk of steel and I say 2 millimeters, that ain't helpful. But it's just fascinating. That's the independent variable in this strain equation. Is like, hey, I have a cylinder and I'm going to tweak it this way and that way, and we're going to get some sort of angle to form. I'm going to be able to measure that, and that's going to be my independent variable. If I measure it to be that 0.001, I'm going to go up on my graph to 10,000 pounds, and I'm going to be like right there. And this graph is going to be totally linear up to 40,000, and then I don't care about it. People are going to lose their lives after that, even though it does something, whatever. But hell yeah, so that's that linear zone, and that's the equation for it. This equation of this line goes through the 0 axis, so this is y is equal to mx, where this is your independent variable. And the slope is g. If I went over 0.001, so always do this. If I go over 0.001 and I get up to 10,000, okay, how many more of these segments do I need to go over to get to the actual number 1? Because that would be a rise of whatever, divided by 1. So I could go over 1,000 of these segments. Okay, so if I do 0.001 and that's 10,000, what's 10,000 times 1,000? That's 10 million. So that's the slope of that line. Because if I actually did go over 1,000 times, I would be at a distance of an angle of 1 radian, which would be nonsensical for these things anyway, because they're small angles, and 0.004 is the linear limit anyway. But if I did, if I just extrapolated this, went over to 1, I would be at 10 million psi. But that's the slope. That's kind of mentally I do that to see that slope. Because I think it's a little bit hard to be like, what's the slope here? Well, it's just rise over run. That's 10,000 divided by 0.001. Dividing by a very small number gives you a bigger number. So that's where we get that 10 million. Hell yeah. And so that's kind of the introduction to at least shear. So we have some sort of idea. Even I just do this for me, trying to get better at being like, trying not to let that symbol just ruin my life. So, hell yeah. All right, and tomorrow or some other day, or I shouldn't set limits because I'll probably just give up. But, yeah, I would like to go over this proof where we actually throw in, but I think, I have a hard time just reading the textbook and just, like I said, saying one thing. I'm not going to do that, so... But maybe tomorrow we'll try, because we just don't get very far. And there's no reason to do an introduction every time, but I have a hard time with that, because tomorrow I'll probably do some sort of introduction anyway. All right, but hell yeah. So yeah, you get your shear, and then you figure out what the hell's going on. But yeah, it's a little complex. Yeah, because if you got kind of one way, you got another way. Just like we were saying, this is kind of fascinating. With the whole idea that if you have this little three-dimensional thing and you're shearing it up and you're shearing it down, guess what? You get these angles to form that way and that way, and so this thing also tweaks out in this sideways diagonal shape. Isn't that interesting? That if we go up and up, here is the Yeah. So here's the square view, and then the side view gets diagonaled. But look at this. The top face is now over here, and the bottom face is way over there. And so those two slide across each other. So in this longitudinal direction, you get that. And we'll finish with this. A chunk of wood has these long lines of, structure or whatever wood's called. But they're very weak, sliding past one another. Wood is like soda straws. So if I take like a 2x4 and I have all those lines, you know what I mean? They're kind of like soda straws where if I push down on them, they actually have a lot of strength. What they don't have strength is, it's weird. If you take a 2x4 and actually apply it, to sandwich, heavy weight, it sucks to take weight. If I put a base plate on that, these are like little soda straws and they'll actually crush flat. So it's not very strong that way. The other way wood is not very strong, I guess we're going over all the ways wood's not very strong. These soda straws can slide past one another. So for whatever reason, if I'm only applying a downward force just on half of this beam, and then this is just chilling in free space, and then let's say the base of this also is, just kind of hanging out, but then that other part is, or that didn't make any sense. But yeah. If I'm trying to shear this piece of wood along these soda straws, they'll just slide past one another. So that's what I'm getting at. So so if you have a 2x4, and I'm trying to take half of it this way and then the other half that way, it can slide past each other fairly easily. Compared to if I take this 2x4, and try to shear it in a vise this way and that way. If I do that into a vise, we're gonna get let's do the picture different. Yeah, and then we're gonna end with this. So if I take this 2x4 and then I want to shear it on that line, I'm gonna do an upward arrow there, a downward arrow there. My diamond shape is gonna look like that. Cool. But it's three-dimensional. And these aren't just going to be vertical. You know what I mean? What's going to happen is my diamond shape is... should I kind of teach you how to draw these? This is the way I do it. So I'm going to kind of have this as my square. If I do shear it upward, this face is going to go up to there. You know what I mean? And then so it's gonna be like right here to right there. When that happens, cool. And then I'm just gonna say this is rigidly attached at the XY axes. So cool. That face goes up, but that creates that moment this way. So I need the arrows this way. So this face actually comes this way, and so it gets to right there. These 2 points have to touch, so then I just kind of box it in. And then this is the shape that you get. This is the diamond shape. And then so we get this, and this. And so check it out. This face is lower. This face is higher. This face is more to the right. Then this face is more to the left. So the top and bottom faces slide past one another, even though the resulting thing that we want to happen is this right face to slide upward and then this left face to slide downward. So if I do have this square bolt, or in this case this 2x4, and I want this to go up and this to go down, the diamond shape isn't just perfectly vertical. And I think that is a bummer on some of the diagrams, that they don't always show this oblique, shape, you know, that's inside the first quadrant, where you get a little bit of angle here. This is gamma divided by 2, and then this is gamma divided by 2. Where if you just show the shape like this, it's an easier way to represent, hey, this is just gamma. But honestly, it's just like, well, let's roll this into gamma divided by 2, gamma divided by 2, and this was the original 90 to begin with. So that's the deal there. So yeah, so if our square bolt is actually this 2x4 and we're trying to make this diamond shape, cool. Like the soda straws of a 2x4 are actually, I don't know, well, let's say they're kind of challenging to shear through, you know. Yeah, enough said. But if this top layer is going that way and the bottom layer is going that way, these soda straws are really easy. Again, we talked about they're easy to slide past one another. So with wood, you will get splits in wood. And the Hibbler book has a good picture of that. Where I don't think this book has anything about that, even though they're talking about it probably right there. So yeah, that's it. Yeah, they don't have a picture of wood. But yes, so if you have a wooden dowel and you're tweaking on it, you actually might, it might rip longitudinally because those soda straw nature of wood are sliding past one another, where it's actually strong to try to shear it in the perpendicular direction. Where longitudinally, it can just split because, you know, they slide past each other, those soda straw-like structure of wood, because wood has those, I don't know, just the rings in wood, and they make vertical, yeah. Anyway, so yeah, enough said, and then maybe tomorrow we'll go through the proofs and the actual kind of like, hey, like we got to this equation, but that's it. But I think that's a pretty good place to be like, okay, I got an idea of like, give me an angle, I can give you the stress. I can give you a max angle, I can give you a max stress. Above that, we're not talking linear and people died. I can do 0. So yeah, so hell yeah. So now we kind of have an idea of that. And obviously we want to know the max, because if I can't go higher than the max, then, and what we're going to see is that with torsion, like, hey, there's 0 in the center and it's max out to the end. So the end is what's the limiting factor, and that's going to be used in the equations. All right. And it requires calculus, and it's kind of fun, but that's going to be for tomorrow. Yeah, we get an integration, you know what I mean? And moment of inertia, polar moment of inertia. And we just get an equation that you could just go and use, but it's just really good to do exactly what we're doing, is just like stepping through the hoops of the fundamentals. So anytime that we hear these terms, we have like a very good idea of what the hell they're talking about from a fundamental perspective. Okay, so this has been another video on torsion, and I think I had a good time. Hope you did too. Thanks for joining me. Hell yeah.